Bienvenue tout le monde. On a aujourd'hui un qui est francophone, mais qui va parler anglais, à cause des autres, pas à cause des autres. Donc, vous avez déjà lu ce qui a été distribué. I will introduce him now in English. I remember, Guillaume LAJOIE is an associate professor at the University of Montreal and a researcher at Mila, and he has two research chairs, one as Steve and one Canada research chair in neural computation and interface.
Yeah, that's right.
His work focuses on the section of neuroscience and machine learning, particularly in understanding neural dynamics, how brain-inspired models can enhance AI systems. He conducts research on predictive and learning processes in neural networks, and today his talk is entitled Beyond Parameters, and it's about learning in context without plasticity in neural networks, which is a sort of a paradoxical condition. And he says he's willing to take questions during his talk as well as at the end.
Yes.
And they can be, et puis ça peut être en français ou en anglais.
Absolument, ouais.
Alors, welcome to, I can't say welcome to Montreal because you just went around a mountain to come here.
Yeah, c'est ça. Alors, merci beaucoup de m'accueillir dans le séminaire. C'est la première fois que je viens donner une présentation à l'UQAM, je crois. Donc, je suis excité d'être ici, surtout justement avec cette vue. So, okay, I'll pivot to English. So, thank you for having me. I'm pretty excited to be around. I must admit, I've seen the program for the summer school this summer, and I was quite jealous because it was quite very packed. So I'm very honored to be continuing in the trace of the seminar series. So today I'll talk about a collection of recent works that addresses, I think, an interesting paradigms that has come to bear in recent years, especially because of the rise of large language models, but also in a context that is well grounded at the intersection of neuroscience and AI in general. And this is the point of view of...
That's something bad. Oops. Oh, that was you. Okay, oh, sorry. You pressed the button at the same time I did, and I thought
So, and the topic at hand I'd like to address is the idea of credit assignment, but without plasticity, which, as was mentioned, might seem like a paradox in the controversial statement, but I would argue is a mechanism that's at the root of a lot of higher order cognition in some sense, and the mechanisms in AI which are capable of reproducing some of these mechanisms. Right? And so, there's a few examples of such mechanisms that are studied in the brain, right? So you can think about, these are some of the examples, right? Context-dependent effects of expectations, optimal coding modulated by arousal, rapid motor learning via inputs, and so on and so forth, right? And this refers to situations where task acquisition might happen on timescales that are much more rapid than synaptic plasticity mechanisms. And there's beginning of work into understanding the circuit mechanisms that might lead to essentially credit assignment. So you can think about, when I learn to play tennis, right? Like when I iterate from one swing to the next to get closer to the ball, it's not just synaptic plasticity that happens, but there's a lot of machinery and sensory feedback that adjust the sort of the task acquisition. And now, later on, the big question is there's a lot of consolidation that happens with plasticity and so on. But I think that's the topic of learning without necessarily plasticity, but with the presence of signals from either the outside world or other places in the brain is, I would argue, very much an active field of research in neuroscience. And in parallel, I would say in recent years, that's been a paradigm that's been proven quite revolutionary in artificial intelligence, right? You can think about phrases that are now common, such as prompt engineering, chain of thought, fine-tuning, zero-shot learning. These are all paradigms in large language models, large sequence models, that essentially do not require parameter changes, right? And so the overall kind of term that catches a lot of the mechanisms behind all of these topics is called in-context learning. So a lot of you might have heard about this. So this is the idea of passing a lot of task instructions in context, i.e. in the prompt to a model, and then obtaining an output of that model without necessarily doing any optimization in between, right? So to illustrate what this means, I have like a kind of a cute little examples. It's kind of a toyish example, but I think it drives home the point, right? So I've asked a model, right? In this particular case, it was a version of ChatGPT. Have you ever heard of the word equi-iso-antonyms? So I've worked very hard in creating this word. This is not a word that exists. If you Google it, it's not been, it's meant to evoke certain semantics, but it's not a word that has a definition. And then the model goes on and tries to give me a definition out of the components of this word, right? Like equi-iso-antonyms are known as auto-antonyms or contra-antonyms, words that have opposite meanings, blah, 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 blah. So it tries to bullshit in some sense, which is to be expected, right? It tries to infer the most likely answer based on that question. But now I give a more precise definition of what I mean by this word, which is, again, a made-up kind of a definition. So what I say is this is not quite right. Equi-iso-antonyms designate pairs of words that have the same number of letters but opposite meanings, which is kind of an arbitrary relationship between concepts. And then I ask, can you give me examples of equi-iso-antonyms? And the model gets at work, right, and provides a list of examples, right? You'll notice that it kind of fails at enforcing the number of letters towards the end of the list, and then you can promptly point that out, and the model adjusts pretty well and can provide examples of this new concept that was essentially presented in context, which was not part of its training set, but which could, it could solve the task by explaining what the task was, right? So this is kind of an interesting example, right? Because, and you can think about other situations where this might happen, where you provide an examples of a task or instructions of a task in context. There's no plasticity that happens in the model, yet there's credit assignment in the sense that the task gets solved, right? And so I'd like to think about the mechanisms that lie behind the this principle, this action in models, and I'd like to argue that that's an important mechanism behind like higher order cognition in general, and would like to lay out a research program into understanding in context learning a bit better, both in the context of neuroscience and in AI. All right, okay, so let's think a little bit about what task of sequence prediction is, which is precisely what these large models are doing. They're essentially just predicting the next token in a sequence, right? The next word in a sentence. So for example, if I ask, if I give in context, the brain is in the model essentially produces a probability distribution over the entire corpus of words and gives a high probability on the next word that would come in this sentence. In this particular case, this toy example, the most probable word would be head, right? Like the brain is in the head, as opposed to probabilities that are assigned to other words, car, forest, store, et cetera, et cetera. And these models, there's a few different variants of architectures on how to do this in AI. The most dominant one these days is called the transformers, and I'm sure everybody's heard of them. But there's also state space models, other types of model. The important part is that the job of the model is to extract statistical structure within the context and then produce a probabilistic a probability distribution of the output, and then essentially you sample the most likely word in that sequence prediction, right? And it turns out that models trained on this simple objective, which is self-supervised, right? In the sense that you don't need labels, you don't need anything. Given sequences, if you mask tokens, the only job is to predict the right look or to predict the property distribution that best models the sequence. And if you do this at scale, then you get something that's quite remarkable, i.e. these large language models, right? So this is an example. Okay, so this is how sequence prediction works. And in context learning essentially leverages the fact that you have these models that are capable of doing sequence prediction, but repackages pretty much any task in this context, right? So I'd argue that sequence prediction is a very general principle because you can take any supervised learning task and repackage it as in context, right? So let me give you an example about this, right? So say I want to do a regression task, right? I have a bunch of examples, X, Y pairs. And the job of regression, right, is to output a model that takes an X as an argument and outputs a Y, right? This is a supervised learning task, i.e. I have a bunch of data point X's and I have a bunch of output point Y's. And I'd like to come up with some sort of model that generalizes well, right? Based on these examples, what's the most likely output given a new query X star? This is essentially the goal of machine learning in general, right? Like supervised learning, given a data set with a bunch of examples, how can you come up with a model that captures that data well and that extrapolates quite well to generalize as well? Well, it turns out that you can repackage this, this task of learning as a sequence prediction, right? So if I pass pairs of examples, X of Y, as different tokens in a sequence, and then I ask, given a query token X star, what is the most likely next token Y? Then essentially I get a model out of this, right? So typically machine learning has thought about this model as parametrically fitting a model to these different points, right? When I do regression, I take a linear model, for example, and I find the best parameters that minimizes the log between the model's output and these examples. In this particular case, it's kind of an implicit version of this in the sense that I'm asking a model that takes in this sequence in context. And in this particular case, it's IID samples, right? There doesn't need to be correlation between the inputs. I can just pass these examples in context, and I get a model that is not necessarily given by gradient descent or by parametric learning. It's done within the activations of model that has been trained on larger data sets to do some general sequence prediction. Okay? So this is an important point, right? In context learning is not only just next token prediction as in language, but it's a paradigm to do learning in general. That's not parametric optimization. So there's this distinction, right? So it's a form of amortized learning, I would argue. So if you think about how large sequence models, large LLM models are trained, you can think about, it's a large language model that's trained to predict the next token given a context, and you've trained it in a self-supervised way on the whole internet, right? So here you have a model G that's been trained on the whole, corpus of written text on the internet. And what is done during this training, this is trained via deep learning. I'm adjusting the weights of a large transformer, say, into minimizing the error in predicting the next token in a large model. But I can take these models and I can do in-context learning. And the model that I get out of it is conditioned not only on the context that I give it, but also the entire model that's learned to predict sequences for which I'm feeding a data set to now, right? So in this particular paradigm, the credit assignment is done via the activations of this big sequence model and not via the weights that have been trained. So I'm amortizing learning in general by having this sort of sequence prediction training and then repackaging supervised tasks to give me a model in context. Okay, does that make sense? This distinction? Okay. And I'd argue that this is actually a very powerful way of doing learning, of doing like machine learning in general. And hopefully I get to convince you that this is worth investigating. So the big difference, and you might have heard these nomenclature in the literature, is, you know, sometimes people call that in weights or in activations learning. So one of which I'm assigning credit via optimization of parameters, and the other one is via just the activations of a general learner systems. And the big question is, how does plasticity and activity-driven learning combine to support high-order learning? And this is the question I'd like to address today. It's start to tease this kind of duality of learning apart. Okay. And I'd argue that there's two main questions at hand here. There's one that's more physiological, i.e. the circuit mechanisms that might enable this type of dual learning to occur. And the second one is in terms of objectives, like, you know, and more about how to train learners to be in-context learners, essentially. And so I'll touch briefly on the first part, which is, if I understand correctly, if I remember correctly, is the paper that was circulated. But I don't think the paper that I'm going to talk about in the second part has been communicated to you, and I apologize about this. It's on the archive now. You can Google it later, but this will be. I can hopefully I'll spend more time here, so you don't need to read it so carefully. So is there?
No, I'm just turning it to so that, yeah. So, nice.
So that's so I get 3 versions. Okay, perfect. Okay, so in terms of the circuit mechanisms, this is where I think there's a lot to learn from studying the brain, in the sense that, like I've mentioned earlier, there's a lot of ongoing research to try to understand learning mechanisms that happen via inputs and not just at the level of synaptic plasticity. Right? These are a few examples of recent papers that touch on this idea. And I think from the point of view of theoretical understanding and deep learning in general, it's important to understand how can neural network learn if the weights are not changing, but only inputs, right? So this is a question we've asked in this paper that's been shared with you. From a mathematical perspective, we're asking, right, are neural networks for which the parameters are fixed, but that are driven by different inputs as expressive as other types of neural networks, right? And so this paper, we essentially derive universal function approximation theorems for networks in which the only thing that we change are essentially constant inputs to the neurons, i.e. bias terms. So if you think about a neural network, you have, you know, a lot of parameters for the connections between neurons, and then there's these kind of additive parameters at the level of single neurons, which are called biases. These are the same thing as like feeding a different constant input at the level of neurons. And what we show here, or the question we ask, is if we change only these bias terms, i.e. only the input to a neural network, how expressive can this neural network be? And so in a nutshell, what we show is both random feed-forward neural networks and random recurrent neural networks, where only the biases are learned, are actually universal function approximators, right? So given any function, you can approximate it given large enough random networks in which the only thing you train are inputs to neurons. And this is different than like a more classical reservoir-like computing, where you take a random network and you tune a readout. Like there's no tuning of any readout here. The only thing that's tuned is inputs given to the network. So there's definite advantages to this, right? Because you can have a single neural network.
Question about the wording. So
oh, yes.
Where only the biases that are learned, the only biases that are learned are universal function.
No. So
this is
we show that, sorry, random feed-forward network and random recurrent networks, i.e. neural networks, where only biases are learned, are universal function approximators. So the networks themselves are universal function approximators. And yeah, sorry, it's a little bit misleading here. I should rephrase this. And so here's an example of some experiments that we show in the paper, where essentially we take a random network and we fix its connectivity weights, and the only thing that we care about is tuning different inputs, i.e. biases to the network, to solve many different tasks, right? So one advantage is you can have a fixed network and do many tasks trained on it. And what we show here is that you can actually equal the performance on fully trained network on a variety of different tasks. So these are a bunch of perception or tasks, like, or image classification. Everybody knows MNIST or KMNIST or fashion MNIST. You basically feed an image to a network and you ask the network to predict the label, like was there a dress or trousers or like digit 5, 6, whatever in an image. And what we compare here is, like, if you take a network and you train basically a different network for each of these tasks, you can, and we control the number of parameters that are trained. So in the case of neural networks where only biases are learned, then we allow the networks to be bigger because the number of biases grows as n the number of neurons in the network, whereas the parameters in the neural network grows n squared as the number of neurons in general. So if we control the number of parameters, then we can show that we can train pretty much competitively on a number of different tasks. But the kicker here is that there's only a single random network in the case of the bias only tuned setting. So the same network can be reused for all of these different tasks. The only thing that changes is a set of inputs that's given to that network. And then we investigate the relationship or how which neurons are activated in the network during different tasks. And interestingly enough, you have shared structure depending on the task. So there's a lot of future work to be done here, like into the structure of the inputs that are actually learned across different tasks. There's, you know, reused features and so on and so forth. So this is corroborating a very theoretical result that these are indeed universal function approximators. So lessons from this work is that fixed networks driven by constant input are expressive enough to do pretty much anything if you have them large enough. It might not be a good idea to do that if you have a specific task and if you have you know, a limited number of resources, right? Because these networks need to be very big in order to get to these tasks if you select them at random, right? But you can reuse the same reservoirs for many tasks by only switching inputs. And then, you know, it's a small detail, but you know, the proof works whether you change the biases or the gain of the neurons themselves, right? And it should be noted that random networks are actually a worst case scenario. If you do have a, you know, collection of tasks, maybe you could learn a little bit of the connectivity weights and then switch between tasks with inputs, right? Which is arguably what might happen in the brain in some of these examples that I've shown you earlier. So the question now becomes, what type of meta-learning, you know, training could we induce on the parameters of these networks in order to then freeze them and use them with input only, right? Which is what brings us back to in-context learning in large language models, right? Because if you think about what's happening in these large transformers, you're essentially pre-training these transformers on doing next token prediction. And so you're adjusting the internal neural networks of a transformer, i.e. the attention head, the MLP, the multi-layer perceptrons that are inside the transformers, in order for them to accept different inputs in context and then give different outputs. Right. So when you freeze the parameters of a transformer, you're essentially freezing the parameters of a big network such that you can then control it only with inputs afterwards. Right. So there's a hint in essentially what we use as objective functions in large language models to achieve just that. Right. Which like this is what I want to talk about now is essentially the power of sequence prediction and what it leads in terms of architecture that can then be controlled in context. Okay. Any questions on this point? Yeah.
Steve Henson.
Yes.
Go ahead, Steve. Can you hear?
Yeah, can you hear me?
Yes. Maybe barely. Yeah.
Hello?
Just a second, we're going to increase the sound just a second.
It's no good?
Just 1 second, there's somebody doing magic here.
How's that?
That's better, yeah.
I can see.
Could you please go back to the last slide?
Yeah, of course.
So a couple things. When you say fixed networks, you mean you're randomly selecting weights and then fixing them?
Yes. Well, in the paper I've shared, this is what we're doing. But what I'm saying is that this is a worst case. Maybe you can select like not so random weights, but still fix them and then do in context learning.
Well, what's the basis on which you'd fix them then?
I'm sorry?
What would be the basis on which you fix them?
Aha, this is exactly the second part of the talk now.
I see. Okay.
Yeah.
Well, maybe I should wait. One thing I would note, since I've been through this since the 80s, we had many kinds of universal approximator theorems due to a number of people, Hal White, others, but Andy Barron, a statistician at Yale, had proven universal approximation, but more in a probabilistic way. And I believe he did this for random weights. So you might check your reference there.
No, we do. I believe we do cite this work. I think one thing that should be noted is that the proofs we present here are very much mimicking the approach of what's called the lottery ticket hypothesis, right?
Right. Yes,
the strong lottery ticket hypothesis.
Absolutely. So my last quick clarification question is the thing we learned in an awful way back then was the universal approximation theorems didn't actually guarantee anything about learning, which Steve Judd and a number of other people began to show
Absolutely.
was complete.
Yeah.
And so
it's just expressivity. Yeah.
The problem, of course, which Yoshua Benjo has had some really good work on, suggesting that there are no local minima in this space if the dimensionality is large enough, whatever that may mean.
Yeah.
And so there's something about the scale here that's important. And I'm all for random kinds of algorithms. One of the original one was called Random Leap, which was done at the labs again back in the 60s. Very similar to this idea to avoid gradient search, but I'll stop there.
Yeah. No, but I think I shared your intuition here, and I have to say, right, that I don't think random networks with tuned inputs is the way to go. What I'm saying is that this is the worst case scenario, and we know that in the worst case you have universal function approximation theorem, which is a good guarantee that if you do a little bit of work on the weights, you can get essentially a good cohabitation of credit assignment via inputs and learning, right? But these two mechanisms are staggered, right? Like it's the same way you do meta learning, where you pre-train on a sort of the meta outer loop, so called, and then you can train on many different tasks in inner loops, right? And I'd argue that this is the mechanisms that are underlying a lot of the large language models. And what I want to talk about next is essentially what you get at the end of it, right? Like if you have a model that's been pre-trained, where then your parameters are fixed, and then you do some learning in context, i.e. with inputs, what is the advantages of the models you get as opposed to just doing everything parametrically? So this is where I'm going, okay? And that's departing a little bit from the more expressivity questions, and hopefully this is going to be enjoyable, but we're going to have to think about complexity in some more like bird's eye view here. Okay. So the work I want to present now is a recent paper, and this is the paper that's now on arXiv. It wasn't at the time where I was invited to present. It's called In Context Learning Occam's Razor. These are the folks that have contributed to this paper. Eric Esmosnino is a student in my lab, also co-supervised in Provencho's lab, who's been leading the work. And this is work in collaboration with Danya Sridhar's lab. So Danya is a professor at UDM and at Mila, working principally on causality, right? And so the big take-home message of this work is that sequence predictions find the simplest in-context learning models, and that the simplest models actually generalize best. So there might be an incentive to actually use pre-trained models in which you have fixed weights that are then driven by inputs to give better models that generalize better than if you were to do it the good old-fashioned way, i.e., doing some parametric training on a data set. Okay, so let me lay down the argument here. But before doing that, we'll need to use a measure called Kolmogorov complexity. So out of curiosity, how many people here in the room have heard of Kolmogorov complexity? Just barely. Okay. Yeah. So this is slightly obscure measurement, but it bears a lot of resemblance to common information content from like the Shannon sort of information theory. But let me lay out like a quick overview of what that measurement is. Kolmogorov complexity essentially refers to an object, or it could be anything, right? Like, but an example here is consider two strings, right? String A, which is 42424242, and string B, which is entirely random sequence of characters. Kolmogorov complexity aims to measure how compactly you could compress a string and still recover its perfect constitution, right? So in other words, you can think about the minimal length of a program that could output that object, right? And by here, like this is where the measurement becomes a little bit weird because you can't really compute it, right? You would have to search over all the space of all Turing complete programs and say, what is the shortest program that can output this string? This would be the Kolmogorov complexity of this object. So for example, if I have like a code here that outputs the string 424242, then it's just a matter of like printing, 42 12 times, right? As opposed to this string here, which does not have any structure, you'd have to hard code the string to output it, right? So in this particular example, you can see clearly that the Kolmogorov complexity of string A is smaller than Kolmogorov complexity of string B. So there's an important link to compression here, how compressed an object can be. So like I said, Kolmogorov complexity is difficult to compute, but you'll see that some decomposition of it can be computable. In some cases, we can make headway without computing these things, which is what I'll show you today. Another component of Kolmogorov complexity is the idea of joint and conditional Kolmogorov complexity. So I can talk about the joint complexity of two objects, X and Y, and I can decompose them in the usual probabilistic sense, right? So this should be familiar for those of you who are familiar with probability theory. So the joint complexity of X and Y can be equal to the conditional complexity of X given Y plus the complexity of X, right? Which leads to an interesting realization, and is that you can now capture the complexity of functions, right? The complexity of Y given X essentially talks about the, can be an object that captures the complexity of a function between two random variables, for example. And this is a good proxy to think about simplicity of an explainer or of a model. So in this particular example, if you have a function A that has, explains these data points, and you have another function B that explains these data points, but it's like way more wiggly, then the Kolmogorov complexity of function B would be higher than the Kolmogorov complexity of function A, which is a way to quantify a good old principle which is called Occam's razor, right? Which I'm sure everybody here is familiar with, that says that in, all things being equal, the simplest explanation is often the best, right? And there's a lot of established like machine learning principles that argue that generalization is best at when model simplicity is at its maximum.
That was Chaitin's interpretation of Kolmogorov.
That's
already.
Right. Yeah, exactly. Yeah, that's precisely it, right? So this is one useful way to actually get quantities to essentially try to bound complexity of the model, which is where we're going with this. Okay. All right, and this is, this is a nice example that I think speaks volume, right? Think about the problem of selectional celestial mechanics, right? If you think about the evolution of our understanding of the world around us, think about, I find this actually quite evocative, right? You think about the ancient Babylonians that kept lunar phase records, and then they could predict just by extrapolating from these big records, like, okay, this is the phase of the moon, so on and so forth. And fast forward a little bit to the time of Kepler, where there was a little bit of, again, keeping track of a lot of celestial movement, but then trying to formulate rules and a few principles by which these things that would explain a lot of these movements. And fast forward to Isaac Newton's and universal laws of gravitation, which are arguably the simplest laws that generalize actually perfectly, right? So here, the idea is that the simplest models that capture the data actually will generalize best overall, right? So if you have a model that relies on the fewest lookup tables and the most simple universal principles, then you're on your way to explain things that in a way that generalize best. Okay, so this is the idea behind.
Generalize best here means really best or fastest or cheapest or whatever.
I mean, best, i.e., like your prediction loss is better.
So the predictivity.
Yeah, exactly. Yeah. Okay, so let's dive a little bit into the math. And I'm gonna go through math argument here, but like I implore you, please stick with me. I think like there's really cool stuff at the end. At least I think so. Okay, so there's an important relationship to probabilistic machine learning that comes out of measuring the complexity of a data set. Okay, so let's start with some data set here, x1 to xn, and let's suppose that these data points are sampled independently from some probability distribution P of x, right? Now, it turns out that, and say I have this model P of x, it turns out that one can compute, actually, this is one of the rare cases where you can show, you can compute the complexity of a data set given a model of that data set. And this is precisely given by essentially the negative log likelihood of that model. So give me a model of the data set, and I want the complexity of that data set, given that I have this model, and I'm assuming that this data comes from that model, then this complexity amounts to the negative log likelihood of that model over the data set. Now, I should point out that this is precisely the loss function that's used to train sequence models, right? So if you think about next token prediction, what you're trying to do when you do next token prediction is given conditional on the context you've seen, you're trying to minimize the negative log likelihood of the probability distribution of your next token, right? So this is, again, like an important, this is the loss function that's used in generative AI nowadays, right? Now, this has, for those of you who are more familiar with Shannon information theory, this is precisely the Shannon information, assuming some Huffman code, right? Now, let's go back to our joint Kolmogorov complexity, right? So I'll remind you that if I'm interested in the complexity of two objects, say the data set and the model that explains it, I can decompose it into these two terms, right? I can decompose it in this term and this term here. Now, I'd argue here that we have an expression for this middle term, right? The complexity of a data set given a model. This is the well-known loss function that we use in machine learning. And then the extra term here is the complexity of the model itself, which is exactly what we'd like to keep low if we want to follow Occam's razor. We want to keep models simple. In general, this is done in ad hoc ways in machine learning. All these regularization, like sort of regularization term on parameters of your models, these are all essentially heuristics to keep complexity of your model low. But what I'll show you today is that there might be ways to bound it just by doing sequence prediction. Now, okay, we can compute the middle term. We're still left with these two terms, the joint complexity of the data set and the model, and the complexity of the model. This is really hard to compute. This is untractable. But what I'll show you is that this we can approximate. Okay. Okay, so this is where we're going. I'm going to unpack this part of the term. This middle one we know. Okay. So to do this, let me introduce the idea of an optimizer or a learner, right? So suppose when you do, say, deep learning on a data set, right? This is the same as saying, okay, I have a neural network and an optimization scheme. And what I do is I feed a data set to this optimization. And then the output is a parameter set for my neural network that minimize some loss function. Okay? So I'm going to define T here as an optimizer. It takes a data set as an input and outputs a set of parameters for some model, right? P of data, which minimizes the loss function that we're interested in. So this is the usual negative log likelihood here, right? So this is, you can think about T as being some version of stochastic gradient descent or gradient descent, so on and so forth. Like if gradient descent is some T, right? So given some optimizer T, what's been shown recently actually is that you can estimate the complexity of a data set and the model that's spit out by this optimizer in the following way, right? So this is called frequential length, right? So this is the last thing I'll have to introduce to get to where I want to go, but it's fairly simple. Right, so the way I'm computing the frequential code length of a data set given an optimizer or learner, right? That's an optimizer and kind of a model class, is as follows. I'm going to take my data set D, and I'm going to take one point in my data set, and I'm going to feed this to this learner D. So I'm going to train a model on one data point, and then I'm going to compute the loss of that trained model on a new data point in my data set. And of course, this model is going to suck, right? It's going to be bad because I've only trained it on one point. It's going to generalize poorly, right? Then what I'm going to do is I'm going to take 2 points, retrain my model, right? I'm going to fit this new data set here with now 2 points, retrain a new model, and then predict the loss on a third point. And then so on and so forth, all the way to the end of this frequential curve, which is training the model on the entire data set, right? And it turns out that you can show that the sum of the intermediate losses when you do this scheme in expectation gives you exactly an estimate of the joint Kolmogorov complexity of the data set and the model class itself. Okay. So, okay, that's kind of a mouthful here, right? But it's a nice way to bootstrap an estimate of this joint complexity term. And so, yes, yeah.
An estimate or best estimate?
Under some condition, it's actually an upper bound on the Kolmogorov complexity. But there's there's details here, but you can think about this as a good estimate of doing this, right? So in a sense, like this is an expensive thing to do if you're doing it on neural networks, right? You need to take your data set at one point, run gradient descent until you get to an optimum, estimate, and then do it again, run it to an optimum with 2 points, so on and so forth, right? So this is difficult to do on neural networks, but it gives you handle on this term, which is the missing thing we were looking at, right? Now you can say, all right, let's parameterize this learner T, and let's try to minimize this whole thing, right? So this is essentially saying, I don't want to like fix an optimizer anymore. I want to get the best optimizer that I can, given these relationships. Now, the desiderata here are T should be fast to evaluate, should be gradient friendly, and an expressive class of optimizers. And what I'd argue here is that this is exactly what autoregressive sequence prediction does in next token LLMs. And here's the picture you should have in mind, is that the parameters here of this learner are precisely the parameters of my big transformer. This is what I do when I train a neural network to do sequence prediction on next token. I'm training an optimizer to take whatever context I give it and essentially give me the best model that explains this context. And you can think about the parameters of that model P as actually the activations that are given a context to this like learner model, right? So this is the relationship here in the context of sequence modeling between the parameters of your sequence models and the activations within the sequence models, right? It's the parameters of a learner that essentially gives you a model that happens given a data set. In this particular case, the data set is fed in context, and the learner has been parameterized for sequence prediction, right? And so this is the in-weights learning I was talking about, and this is the in-activation learning that's been talking about. Okay, now, going back to this frequential code length, right? As I showed you before, this is essentially computing the joint homograph complexity between some data set I, which now is essentially the context that I'm giving to my network, and the joint of the model. So if you unpack this, what you get is the following. Remember, this joint here can be decomposed as the conditional complexity of a data set given a model, plus the complexity of the model itself. Now, this guy here, we know it's just essentially the training risks, right? So the negative log likelihood of the model itself. And this is the thing we were interested in. So it turns out that if you do sequence prediction, right, i.e. frequential length minimization, what you're doing is you're jointly minimizing both the loss of your task given in context and the model complexity. Right? If I were to remove this, this is what's been done in standard meta-learning so far, right? So if you have meta-learning, i.e. like I'm trying to get one model that does many different tasks, and I train on the loss of all these tasks all at once, then I get, this is precisely this. But I'm arguing that if you do this in a sort of next token prediction way, right? Like you trying to jointly minimize not only the loss on the entire data set, but on parts of the data set as the data set grows, you're essentially jointly minimizing both the loss of the data set and the model complexity. So this is the main story here, right? When you do next token prediction and you use the model itself as a learner, given a data set in context, what happens is that you're jointly minimizing task error and the model complexity, which is why I think it's no accident that in context learning, i.e. like these big large language models, when you explain tasks, works so well, right?
Could you just intuitively give me a sense of what you mean by plasticity?
So, okay, so plasticity here means like that we're changing parameters of a network. And what's been done here is we're essentially changing the parameters of an optimizer, a learner, that then takes a data set in context and then essentially finds implicit parameters of the model that's fitted to that data set via the activations that are given by that prediction. Right? So plasticity in this case, I would say, has been done once at pre-training and general sequence prediction. And then credit assignment in context happens via activations. Nothing changes plastically.
Okay, so that's okay. So
Yeah.
that's curtailed at that point.
Exactly. Right. So now I'm realizing I'm running low on time.
All right.
But I can, essentially we have simple experiments that corroborate this, right? We compare both frequential objective, i.e. minimizing sequence prediction, in this ratcheted way versus just training all at once. And then we show that essentially, and comparing also to stochastic gradient descent, and you can show that generalization error, especially when you have low data regime, is much lower if you've retrained on these objectives, which is by all accounts, what is done already in large sequence models. But we argue that actually this might be a better way to do machine learning in general, right, than just standard optimization, right? So in the future, you might, one might see is essentially, instead of, if you have a medium-sized data set, instead of doing deep learning on a neural network that trains on your data set, is you go to a giant pre-trained model and you do training in context. Now, the big question is, how do you extract a model that's usable after that, which is kind of a big model distillation problem that is under heavy study.
You feel like taking a question on that?
Sure. Yeah.
Go ahead, Steve.
Yeah, thank you. That was interesting. However, the sort of Kolmogorov story you just told is kind of justification for using regularizers, right? So if we think of a standard regularizer, Aka-Iki or something like this, this is exactly what it's trying to do. It's trying to minimize loss and minimize model complexity. And if you think of what happens in most deep learners or in transformers, we actually apply specific weight decay regularizers as well as what I call stochastic gradient dropout type methods on the deep learning parameter space. So essentially, it's already doing a lot of this, what you are calling regularization in this more theoretical and more principled way.
Yeah.
I'm not sure what I'm looking at them. Why is this an improvement over me running?
That's absolutely correct, right? And
okay, hold it. Go ahead.
yeah, the reason why it's an improvement is that these regularizers, as I've mentioned before, are heuristics that essentially aim to get compact models. Here, the argument is that under the assumption you have a learner T that's expressive enough to find an expressive enough class, you're guaranteed, like, I think the argument here is that you're getting to the best compressed models because you're jointly minimizing the complexity and the task itself without having, sort of roundabout way of getting compact models, right? So the argument here is that this is done optimally and implicitly as opposed to ad hoc ways, right?
Right. But of course, that's asymptotic. And the whole point of the ad hocness, if you will, of the regularizers was these are things that would work in some kind of computational practical context as opposed to, having infinite amount of computation in time. So although in theory you're right, in practice we've seen even on, trillion weight LLMs that the regularizers that we do use, simple weight decay from the 1990s and dropout from the same, from more recent times, seems to provide much more adequate results than if you remove them. Now you could argue.
Okay. Yeah, but I'll stop you right there because there's a distinction here. You can still use these ad hoc methods to train the pis, right? So if you train your transformer, this is not the model I'm talking about. You're training the optimizer. The transformer is the optimizer that gives you an implicit model that's computed in context. So the biggest comparison you should make is given a finite data set, say of regression, right? Let's take that as an example. Either you train a neural network with regularizers directly on this data set, or you take this data set and you feed it to a sequence model that gives you a prediction that's been done in context. What I'm arguing is that the sequence model is an optimizer that's better than gradient plus regularization. And you're absolutely right. We like, this is an asymptotic argument, right? Up to now, we didn't have the expressivity class or the model class to actually search these optimization landscape. And now what I argue is that we're starting to see this with these large sequence models. So the training of the sequence model is still a deep learning problem. You still use regularizers, you still do credit assignment by optimization and gradient descent. But the objective that's learned there is it's not just sequence prediction, it's actually an optimizer itself, such that you can, if you feed a data set to it, you get a model out of it that's not given by a gradient descent. Does that make sense?
No, but I'll let you go on as you have more stuff to do here.
Well, I'll these are a bunch of experiments that corroborate this at a toy level. We also have some results on non-IID data because this obviously was one of the big assumptions is that your data comes IID, right? And then we showed that this works quite well. We also have ongoing work that shows that these ICL-based models are actually generalized best because they might find more compositional solutions. I'm happy to talk about this. But in summary, like this is the take home, right? So it's parametric training of sequence model learns an optimizer T, right? And given a context, i.e. a data set that you pass to that sequence model, your sequence model generates a model non-parametrically, and that the way that this the sequence model is trained via cumulative sequence prediction actually biases the models that you get out of this optimizer to be the simplest possible, which gives you better compositionality and generalization, right? So this is the theory here. And there's different ways why this might be useful for AI. You know, I'm gonna go through this. If this is true, then we have this is promising work that we do in collaboration with folks at Google, where we mix both sequence prediction via activations of a transformer and some good old optimizers. So these are hybrids method that aim to essentially accelerate inner optimization. And so, you know, and I know I'm out of time here. I'm just going to run through this. The idea is that, you know, at the end of the day, neural networks are special, right? They're expressive, and there's a unique relationship between weights and activation.
Okay, because you took questions during this sequence, so your time is
Still 30 minutes.
It's still 30 minutes? I thought it was until 11:30.
Until 12.
Okay. I'll have to leave a bit earlier, but yeah, I'm happy to take
It's not compulsory to 12, it's just optional.
Okay, great. Yeah. Okay, so let me give you like the big picture here, and then we can talk about whether this is a valid story or not, right? So I'd argue that there's something special about neural networks beyond the universal function approximation that they offer, and that they're expressive in different ways, right? Both parametrically and non-parametrically, given the fact that we can have growing capacity for context now. There's a unique dual relationship between weights and activation inputs, and that the details about architecture are flexible, right? So what these experiments I've shown you are on transformers, on RNNs. As long as you can train a system on sequence prediction, you can do in context learning, and you see hints of these advantages in terms of Kolmogorov complexity. Second, and you know, you also see this actually, you're starting to see experiments that look at this in the brain, right? So there's this recent preprint that I think is fascinating, where researchers here show that prefrontal working memory and hippocampus episodic memory can be decoded both in activations and in stored weights of the network. So there's this, you know, like glimmers of this duality in the brain. The second is that sequence prediction is special, right? By virtue of the fact that you can repackage pretty much any supervised learning task as sequence prediction, then you have a general self-supervised objective in order to train these general purpose optimizers, which are these big sequence models. And then lastly, I'd argue that if this is true, then, you know, context access becomes key, right? Right now, there's an arms race in large language models to get bigger and bigger context access, right? Like 1 million tokens, 2 million tokens context. And there's something special about how the brain does it, right? Like, and there's you know, the brain compresses context that we've seen throughout our lives in memory that can be then rapidly loaded up to do some credit assignment without necessarily plasticity, right? Like when you're answering a question, when you're studying for an exam, the question you're given is, you know, calls back on your implicit knowledge, loads this up into your memory, and then you execute a task, right? And so there's all kinds of these things which I think if we understand better from neuroscience, we can maybe get out of this brute force era right now. We're just trying to grow context of transformers and attend to it all at once, which is highly energy, you know, hungry, and frankly, like I'm not quite seeing how we're getting out of this ever scaling. And so these points are, I think, an important target for the intersection of neuroscience and AI, which I think we should pay attention to a little bit. All right. So with this, I'd like to thank you for your attention, and I'm happy to discuss a bit.
Or Steve is asking much more complex questions than I can ask, but can I ask you one naive, intuitive one, which is, does this increase or decrease or leave untouched the things that we might be worrying that OpenAI is hiding from us?
Oh, wow, that's a loaded question. What do you mean, like, so I'll tell you right now, OpenAI, I think, is betting big on just scaling inference, i.e. scaling context, right? And so in some case, it's a validation that there's actually a bet that bigger context capacity enables more general learning, right? Now, I don't know exactly what you were getting to with that question. I'm unclear if schemes that directly target this implicit pressure on, in-context model complexity are being leveraged. Yeah, this is some stuff that we're trying to get into at Google, I would say.
Est-ce qu'il y a des questions ici? Regardez, moi j'ai vos questions. Et vous le savez, ce que vous avez posé. Est-ce qu'il y en a qui sont encore actuelles? Tout a été réglé.
Je pense qu'il y en a sur la.
Ah oui. OK, go ahead, Steve.
Or there's yeah, oh yeah, Steve.
Quelqu'un
Yeah.
d'autre? Okay.
No, I'm happy. Like,
Okay, Steve, go ahead.
Yeah. Okay. Yeah, that was a great talk. Very theoretically, I think you're onto something here, but I'm not sure I understand how this works. So let's do a little kind of thought experiment. That now I just joined OpenAI. Let's say I haven't, and then I'm going to quit in a month, like everyone. And so, what am I going to do with your analysis in a production way? What exactly is the non-parametric, the non-parametric kinds of algorithms I'm running here? I'm agreeing at the top level with everything you're saying, but I don't see how this changes the training of a 100 billion weight model. I just don't get it.
Yeah, so you're absolutely right. Like, actually, by many measures, this is merely a normative account as to why what we're doing now works well, right? What I'm saying is that the current way of doing sequence prediction is actually a really good idea if what you want to do is to learn stuff in context, right? So in a sense, like I'm saying, like, if you're at OpenAI and what you're doing is training big models on sequence prediction, thumbs up, that's the right thing to do, right? What I think, again, like articulating why I think this is important for the future is that it's not only for interactive chatbots or sort of just, like querying, like exchanges with folks that I think sequence prediction is useful. I think that there might be a world where machine learning is now done with these big sequence models, right? So you can imagine a situation where in the future, you have a medium-sized data set of a certain task you want to, whatever, like do like image classification on your data set. And so instead of doing deep learning on a neural network on your data set, you would go to a massively pre-trained sequence predictor, not just on language, but on general sequence prediction, and pass that data set in context to then get a machine learning model that I think, if we believe this theory, might generalize better by the virtue of the fact that it's kind of low complexity. Now, the big question is like, you don't want to, like, sounds impractical, right? Because you need to load your data set in context every time you want to do inference, which is why I'm very bullish on approaches that aim to distill models out of context plus a sequence model. So if we figure out how to do this, then this is, by all accounts, a possibility for machine learning 2.0, right? Like, forget about deep learning your bespoke neural network on a data set. Pass that data set on something that's been trained on everything in nature, right? Like, and extract the right structure to get your predictive model that way. So anyway, like, this is highly speculative, but this is what I would answer.
Okay. Yeah, I think it makes sense now. But then your argument for prediction, sequential prediction, let's call it time series prediction or something, but it has some kind of grammar implication here. There's so many other kinds of tasks that humans learn with. In fact, you could argue the cerebellum is in fact exactly this kind of thing, where it's predicting various states of cortex. And this is happening constantly, and it builds a small, sort of low complexity model of what's about to happen next.
Yeah.
One of the things we know from Anthropic's kinds of analyses of the internals of LLMs is there's somewhere between 60 to 75 million different cluster spaces. And the cluster spaces are very, very specific, like, guilt and regret and things that you should have done or not done, or being, in a catch-22, and, just very weird little small cluster spaces. And so arguably the actual object of interest here may not be the particular next item, but the context that you're trying to learn. In other words, as you bootstrap up these contexts, you should probably focus on the context you have, that is, use that internal structure to make predictions about new contexts that might be useful, which I think is more likely related to the actual neuroscience of the brain. But I get your point, and I like the theoretical argument, at least.
But so, okay, the parallel, again, I think there's a distinction to be made here, because I think the parallel you're making is actually, what activations are responsible for what are actually an argument for the in-context model. Given a context, or given like a prompt or whatever, you can look at the internals of the model and the way it generates your in-context model, right? And that's different from saying, sequence prediction is, in a sense, your meta objective. This is the way that evolution led to how the brain is right now. So think about training the weights of your neural network as, the evolutionary pressure of just predicting the future, right? To not die and so on and so forth, right? Like to predict the predator that's going to eat you and so on and so forth, right? So my point is that these low-level objectives lead to highly capable in-context learning, like model producers, right? And so when you inspect the activations of transformers given a certain context, what you're inspecting is the result of having a system that's been trained on low-level sequence prediction, but then actually is implementing a certain computation on the context you're giving it at the moment, which is kind of a slight this dual distinction that I was talking about here, if that makes sense.
Yeah, it does. I think you're putting all of your candy in one Halloween basket here, and I think the concern here is, as you look at a more micro analysis of the tasks that, say, biological systems do, certainly prediction of the next thing is very important. But even in foraging studies, going back to where animals are foraging and they have a specific risk that they're balancing between predation and not being observed and getting back to the nest as fast as possible with whatever they got.
Absolutely.
So this is a huge multivariate problem in terms of, again, it goes back to the model space that you're in, what I would call the context space that you're in, and the way in which you're trying to generalize that over the cases of risk that you have, before you're eaten and then your model's gone.
Yeah, absolutely. And I mean, okay, like this is like high level arguments, right? And of course, one could argue that a lot of the granular solutions that evolution has come up with are stemming from this low level type of prediction objectives. But then again, like this is highly speculative. But I think you're right. Like there's all kinds of layers here, right?
Yeah, maybe it's an interesting supposition, and I guess we'll see how this plays out.
Yeah.
Since I read between the lines that you have another appointment.
Yeah, I need to run, but I think there was one question in the room, and
Il y en a une. Elle est pas, enfin, au niveau, avec les questions que Sylvain me posait, c'est plus, enfin, de la curiosité. Quand vous avez avancé, fait plus tôt, après 10 séquences, vous avez décrit que la plupart des tâches en machine learning, on pourrait regarder pour les mettre dans ce format-là.
Oui.
Alors, dans ce contexte, je comprenais que c'était comme une bonne majorité, mais qu'il y avait quand même des outliers, naturellement, qui ne pourraient pas rentrer. Mais là, en répondant à Stephen, c'était on est dans la possibilité dans le COPS de pouvoir atteindre la leçon 2 de machine learning, d'être capable de pouvoir révolutionner les paradigmes. Les tâches outliers, pour ça, alors dans l'idée, il y a un moyen de les interpréter, de les retransformer en sequence prediction, c'est juste qu'on n'a pas atteint, ou c'est plus comme ils vont rester en version 1.0, enfin, ils ne sont pas assez importants à toutes les améliorations qu'on peut avoir dans le paradigme.
Je pense que l'analogie peut. Je pense que jusqu'à un certain point, n'importe quelle tâche supervisée peut être packagée en sequence prediction. J'essaie d'être assez plus conservateur dans mes statements, mais en gros, puis, just to answer the question, general audience, like this is highly speculative, right? I'm not saying this is exactly what's going to happen. What I'm saying is that these are interesting questions that actually emerge from these properties of sequence models that do very well in context, right? And it's a possibility, right? And some of this work points to the fact that there might be universal principles that argue that, you know, general sequence prediction, then repackaging as learners for repackaged tasks that are supervised has some advantages. Now, I'm not saying this is going to happen tomorrow. I'm not saying it might not happen, right? We might be wrong. But this is certainly an interesting avenue that was not possible before these large sequence models.
Okay. Well, with that, I really do want to thank you.
Thank you.
Quand je parle de secret, je veux dire que OpenAI n'était pas en mesure de cacher le sequencing parce que c'était dans le domaine public. Est-ce qu'il y a quelque chose?
Oh, so, well, I'm not an OpenAI, so I don't know exactly what they're doing. That's like a secret sauce. But I do believe that a lot of the advances we're seeing is pretty much just scale and small tricks.
It looks like
So, yeah. Thank you.